preparatory cavity here.
Aloha, my name is Nikki, and this is my project, Water Flow as a Key Driver in Coral Restoration. And you guys are the first one to do this actually in a peer review science paper. So, could I see show of hands of who likes coral or the ocean or exactly snorkeling? Awesome, me too. So I got involved in coral restoration a couple of years ago, and I fell in love with coral. And the more I learned, the more I was exposed to the realities of restoration and how expensive and how difficult it really is. And so I learned that there are so many gaps in our knowledge when we're actually doing restoration, and how sensitive corals are to the environment. So I set out to kind of solve these unsolved questions. So I introduced myself to the head of the coral lab at Woods Hole Oceanographic Institution. And she introduced me to their fluid dynamics director, and she let me use her hydraulics lab to conduct my experiments. And I spent this whole summer in Cape Cod conducting around 60 experiments where I took around 15,000 images. So I set out to answer these questions of how does the flow of coral influence the survival of coral reefs, and how can we implement this knowledge into coral restoration? So for my prior research, I actually was researching the specific way of seeing the flow around obstacles. So here it's kind of just a cylinder, and they were using a rotating tank to kind of, I guess, analyze the eddies behind it. And I also analyzed kind of coral morphology and how that plays into fluid dynamics. And so there's actually something called a thermal boundary layer, which is a centimeter above a coral, which essentially traps in heat and old nutrients right around the coral, which kind of suffocates the coral, which could cause bleaching and damage. And so this kind of proves how essential flow is to kind of flush out that boundary layer and bring in cool water and more nutrients for oxygen and nutrient exchange. So this led me to my objectives and hypothesis. So my goal was kind of to discover the insights in coral and flow dynamics and restoration, and to combine my research and discover novel and practical insights. And so I hypothesized that flow velocity, coral morphology, and the coral orientation would significantly affect water exchange and creating either beneficial or harmful vorticities for separate colonies. And these results could inform optimal placement and orientation for the replantation of coral colonies. So this was my experimental design. It was kind of complicated and very precise. So this experiment was conducting on this rotating table that you see here, and there was a tank that was filled with water and dyed black, and a digital camera and a gradient was placed on top of the table, and resin coral models were placed into the tank, and the motor spun at a specific speed until the water reached equilibrium. And once that water reached equilibrium, I would then speed up or slow down this tank to three different speeds, which was 24 RPM, and 40 RPM, and 75. And the RPM was just the motor, so it's not actually the tank. That would be very fast. Then I took around 15,000 images total, and I processed them using MATLAB. So the methodology that I use is called allometric imaging velocimetry, or also known as AIV. And so what it does is it looks at the surface of the water, and it sees the kind of change in slope of this water. And with every pixel of the gradient that was shined above it, it measures that specific slope and can quantify that into velocity and other changes in the water surface. And so from my results, before I started doing my experiments, I calculated a Reynolds number, so I could estimate what kind of flow I wanted. And there's three kinds of flow with this Reynolds number. There's laminar, transitional, and turbulent. And so laminar is more calm and smooth, and turbulent is kind of more chaotic. I also, for the Reynolds number, I calculated it at the end again to make the experiment more precise, and all the calculations very precise. And just before I kind of head into the data, which is a lot, To be extra clear, this is the brain coral that I used and the branching coral, and this is the dense coral. So this was kind of what the velocity field looked like once I placed it into MATLAB. And so what happened with the brain coral, which was really interesting, is if you see this black line, which is the turbulent flow, the eddies that go around the coral and push, so this, in this image, blue water is essentially cool water. And in the simulation, I was able to put particles to kind of see what was going on with the velocities. So the red particles were kind of simulating the heat that was trapped behind the coral. And when the simulation ran, the red dotted line, which is a region of interest, you can see how the eddies actually go around the brain coral, and because they're so large, create this backflow, which essentially flows that water back into the back of the coral, causing stress. And so you can kind of see, especially in this graph, how great that proportion was in this specific experiment. And then for my other corals, it did actually a lot better in turbulent flow, but did worse in other kinds of flow. So for example, this branching coral, it took a while for the laminar flow to actually flush out that hot water. And the transitional flow did well at the beginning, but actually there was some backflow caused at the end, where you can see that kind of crossover at the end of the graph. And for the dense branching coral, it did really well. It actually was also slow in flowing out the hot water, but for the turbulent water, it did really well at first, flushing out almost all of the hot water, and towards the end, with backflow, it was actually ended up going a lot higher. So this is kind of putting all of the corals into one graph. You can see as the brain coral did actually very well in transitional flow with minimal backflow, which is really strange because in the turbulence, it had the big eddies, as you remember. And in the dense coral, the dense branching actually did the worst in this transitional flow, but did well in the others. In this graph, you can kind of see this is where the brain coral did a lot. It had these big eddies that pushed the water back into the coral. And the dense branching did really well at first and actually became higher, and the branching did really well overall in turbulent flow. So for the orientation of corals, I thought it was going to play a large effect in how this flow was able to flush out the water. But in the end, when I put the corals into the tank, I oriented them either parallel or perpendicular to the flow. And so what happened is there actually wasn't as big of a difference as I thought with either being perpendicular or parallel. And you can kind of see in this graph that they show actually a similar pattern. So for water, for overall, this is kind of like, it's really important to know how the flow of coral affects its survival. And so, so the results actually show a really strong connection between like health and flow dynamics. So the combination of flow regime and coral morphology play a large role in how exchange occurs around coral and adjacent colonies. On the other hand, the orientation, as I said, kind of remains unclear. So for the dense branching coral, there was one experiment where it's essentially symmetrical, but it's a little more oval, and it did a lot better when it was parallel to the flow than when it was perpendicular. But for the branching coral, it really didn't make any difference. So overall, kind of morphology and flow play a bigger role rather than the orientation of the coral. So implications. My results actually have really exciting implications into restoration efforts and coral farm design specifically, and how coral reefs can adapt to flow. And so restorations kind of continue to struggle with a lot of deaths, a lot of bleaching, with the water temperatures rising, and ocean acidification. And with learning more about how to design these specific farms or replantations, it's able to actually grow and able to flourish in different scenarios. And being able to kind of see how flow really affects coral is really interesting. They also, we're able to see how branching coral differs from brain coral, and different types of coral affect the flow of water around them differently. So for example, like the brain coral promotes rapid water exchange, with like water mixing between it and its neighbors, while the brain coral the brain coral has that backflow, which could potentially starve its colonies in its wake. So limitations, of course, because it was in a controlled environment, this isn't as applicable to the open ocean, which has a lot of different currents and turbulences, while this controlled environment was just changing the flow in one direction. And this could be a lot more beneficial kind of looking at coral farms or growing coral or in a contained environment, but it's less applicable to the open ocean. So my next steps, I'm actually already conducted these experiments, but because I put multiple corals in a tank, it's a lot different to calculate. It's a lot different to code and to calculate these things in MATLAB rather than just having one coral. And so we were able to have these corals. I was able to see how one coral's flow affects another coral, and seeing how this can be applicable to any other farming and any other experiments. But this data is still being tabulated, and with this data, finally, I want to be able to apply this in restoration trials and be able to actually create a model of what I think would be the best design of coral replantation, which kind of looks like this. It's a little rough drawing of what I think would be the best scenario for coral orientation. And so, brain coral with their big eddies could provide optimal flow for branching corals, which create little turbulences behind. So having these corals next to each other could strategically position and optimize the flow for each coral in the survival. As we know, with the thermal boundary layer, we need the flow in order for them to survive. And thank you so much. And these are my acknowledgements. I'd love to thank the JSHS reviewers and Dr. Chang for organizing, and for Dr. J and Dr. and Dr. Claudia and Dr. James for mentoring me through this process.